So chemical reactions involving acids and bases usually illustrate a general pattern of reactivity. So for example, electron-rich species react with electron-deficient species. Bases are a good example of electron-rich species because they contain lone pairs of electrons and pi bonds that are capable of forming a bond with hydrogen atoms. Acids, on the other hand, are considered electron-deficient because they contain electron-deficient sites. So when you look at hydrochloric acid, for example, it's an acid because hydrogen is the acidic site. It's electron deficient. And so acids, which are electron deficient, will react with bases because they are electron rich. So here's a few things that you should remember regarding acids and bases. Common acids and bases introduced in general chemistry are used in the same way in organic reactions. So hydrochloric acid, sulfuric acid, nitric acid are strong acids, and hydroxide ions, or any ionic compounds containing the hydroxide ion, are considered a strong base. When you only have one starting material, a reactant, containing a hydrogen atom, it must be the acid. And if only one starting material has a lone pair or a pi bond, then it must be the base. Because, again, a base is electron rich and they contain lone pairs and pi bonds, double bond or triple bond. And the third one here, a starting material with a net positive charge is usually the electron deficient acid, whereas a starting material with a negative charge is usually the electron rich base. So let's take a look at some scenarios here on how to identify the acid and the base in a typical proton transfer reaction or acid-base reaction. So this first scenario here, we have one reactant that has a net positive or a net negative charge. So over here, there's only one that has a net negative charge, which is considered the base. So you have lone pairs on the nitrogen and a net negative charge. And so right off the bat, this is the base and this one is the acid, even though this molecule itself also has electron-rich sites. Like for example, this oxygen right here contains lone pairs of electrons, but because this molecule also contains hydrogens, so for example, this carbon right here contains two hydrogen atoms, and so do these carbons over here. They also contain hydrogen atoms. Then that would make molecule A the acid and molecule B the base because, again, this has a net negative charge. The second example here, we have one reactant that is an inorganic acid or an inorganic base. So anything that does not contain a carbon atom is considered an inorganic acid. If they contain carbon atoms, then they could be considered an organic type of acid. So in this case, we have an inorganic type of acid, and this is a strong acid. And when you look at molecule C here, this molecule also contains hydrogen atoms, but because they're bonded to carbon atoms, they're considered weakly acidic acids, weakly acidic sites. And so most likely this molecule will act as a base because of the fact that this oxygen atom contains lone pairs of electrons. And the last scenario that we have here, we have one reactant that contains a lone pair. And so automatically this reactant right here, which is the only one that contains a lone pair, will be considered the base because this lone pair is capable of forming a bond with a hydrogen atom. So this molecule right here, molecule D, is the acid in this case because it doesn't contain any lone pairs and it has multiple hydrogen atoms bonded to the carbon atoms. And here's practice problems number 5 and 6. Decide which compound is the acid and which is the base and draw the products of each proton transfer reaction. So another term for acid-base reaction is proton transfer reaction because of the fact that you're transferring a proton, a hydrogen ion, from one reactant to another. So let's take a look at this first one right here. So we have a molecule containing lone pairs of electrons on the oxygen and this oxygen as well. But then you look at this second species right here, this contains a negative charge, a net negative charge. So right off the bat, this species will be considered the base. And then the other one will be the acid. All right, and then it says draw the products of each proton transfer reaction. And so this hydrogen right here that's bonded to this oxygen will come off, and it will form a bond with this oxygen right here, which is the basic site. And so the product looks something like this. So you have an oxygen that's now bonded to a hydrogen atom, which basically came from this molecule, this hydrogen, and then it's bonded to a CH3. So you have two lone pairs here. So that's one of the products, and the other product would be basically this without the hydrogen. And so let me just draw that really quickly. So we have something like this, double bonded oxygen, and then 3 chlorine atoms, then an oxygen, and then when you remove a hydrogen from a neutral molecule, you add a negative charge to it because it's gaining a lone pair of electrons, 2 electrons. And so you have a negative charge here. So these two are basically the products of this chemical reaction. And this second chemical reaction here is essentially similar to the first one, where you have a net negative charge on one of the species, which is this one right here. So this is going to be your base, which in this case, this is going to be the acid. And with this type of chemical reaction, you can even use curved arrows to show the movement of electrons if you like, even though the problem didn't really ask for it, but I think it's a good practice to show how the electrons move within a chemical reaction. So with this one, you have this lone pair of electrons that will attack this acidic site right here, this proton. And so these 2 electrons here, the bonding electrons, will turn into a lone pair of electrons, and it will go to this carbon right here. And so the 2 products that you get would be hydrogen gas, right, H2, because it formed a bond with hydrogen. And then the second product would be this molecule minus the hydrogen. So we have a bond here, then 3 chlorine atoms, and then a triple bond. And then, of course, this carbon right here will have a lone pair of electrons, and now it will bear a negative charge because we remove a hydrogen from this carbon. All right, so these are the 2 products of this chemical reaction here. And the third one here, we have an inorganic acid, which is basically a strong acid, hydrochloric acid. So this is going to be the acid, and automatically the other molecule would be the base. And so this is a base because of the fact that this nitrogen atom has a lone pair of electrons. And so you have a hydrogen bonded to a chlorine. And so to show you the movement of electrons, you have this lone pair of electron that will attack this hydrogen right here. And then this bonding pair of electrons will go towards this chlorine atom. All right, so what you have is this product right here. Now with 3 hydrogens. And then this nitrogen will bear a partial positive charge. And then we have this chloride ion as one of the products. All right, and that chloride ion, of course, bears a negative charge. And so if this is the acid, then that must mean that this is the conjugate base right here. And if this was the base, then that must mean that this is the conjugate acid. This last example here is very similar to the third one because we have a sulfuric acid, which is an inorganic acid, a strong inorganic acid. And so we're going to label this the acid. And so this one would be the base. So this alcohol right here, this molecule can act as a base because of the fact that this oxygen atom has two lone pairs of electrons. And so you have a sulfuric acid, so the two electrons, the lone pairs, one of the lone pairs of electrons will attack one of the hydrogen atoms. And then the two electrons from the bonding pair will go towards the sulfur. Okay, and so now we have one of the products would look something like this. We have this oxygen now bonded to two hydrogen atoms, and it will bear a positive charge. And you can always double check that using the formal charge equation. And then this sulfuric acid will now have one less hydrogen, and so it would look something like this, HSO4 with one negative charge. All right, so these two are the products of this chemical reaction. What about this practice problem number 6? Draw the products formed from the acid-base reaction of hydrochloric acid with each compound. So if we're reacting them with hydrochloric acid, then every single molecule listed here will act as a base. So the first one here, we have basically an alcohol. So we have a hydrogen and a chlorine, hydrochloric acid, and this oxygen right here contains the basic sites because it contains lone pairs of electrons. And so it's going to attack this hydrogen here, and then the bonding pair of electrons will go towards chlorine. So chlorine already has 3 lone pairs of electrons, and so this becomes a chloride ion. So Cl with a negative charge plus, let's say we have 1, 2, 3, 4, 5 carbon atoms. 1, 2, 3, 4, 5 carbon atoms. And then the oxygen that's bonded to 2 hydrogen atoms with a lone pair of electrons and a positive charge. So that's for part A. What about part B here? So when you look at this oxygen here, this oxygen contains 2 lone pairs of electrons. So let's just draw in, 2 lone pairs of electrons. And then this will react with the hydrochloric acid. And one of the lone pairs will attack this hydrogen. And then the bonding pair of electrons will go towards chlorine. So now you have something like this. And then this oxygen will bear a positive charge. And then you have the chloride ion as one of the products as well. All right, so let's look at part C. So when you look at this nitrogen here, it actually has a lone pair of electrons. And so this is going to act as a base, and then it's going to react with hydrochloric acid. And again, this lone pair of electrons will attack this hydrogen, and then the bonding pair will move towards the chlorine atom. And then what you have is this product right here. So you have a nitrogen that's now contains a hydrogen and then a positive charge. And then of course we have the chloride ion, also one of the products, with a negative charge. And the last one here, when you look at this nitrogen, it also contains a lone pair of electrons. So we're going to put a lone pair here. Whoops. There we go. And then we're going to react this with a hydrochloric acid. And so again, this lone pair of electrons would attack this hydrogen, and then the bonding pair will turn into a lone pair. And then what you have is this molecule here. So now we have a nitrogen that's bonded to two hydrogen atoms, and this nitrogen will now bear a positive charge. And then don't forget about the chloride ion with a partial negative charge. All right, so these are the two products of this chemical reaction between the hydrochloric acid and this molecule here. So you learned in general chemistry that there's a lot of different ways to measure the strength of an acid. You can look at a pH paper, right? So when it turns blue, then you know that it's basic. When it turns red, then you know that it's acidic. And if the acidity is below 1, or if the pH value is below 1, then you know that it's a very strong acid. You can also measure the strength of acid using the concentration of hydronium ion in solution. You can also look at ionization constants. So an acid that's 100% ionized is considered a strong acid, whereas an acid that ionizes partially, like hydrochloric acid, for example, would be considered a weak acid. Or you can also look at ionization constants or equilibrium constants like Ka or pKa to determine the strength of acids. Acid strength is the tendency of an acid to donate a proton, to donate a hydrogen ion. The more readily a compound donates a proton, the stronger that acid is. Acidity can also be measured by what they call an equilibrium constant. So when a Bronsted-Lowry acid is dissolved in water, an acid-base reaction occurs, and an equilibrium constant can be written for that specific chemical reaction. So for example, we have this general acid-base reaction here, where you have the acid reacting with a base, and you get a conjugate a conjugate base and a conjugate acid. And so you have the starting materials on the left-hand side of this equilibrium equation, and you have the products on the right-hand side. So whenever you're coming up with an equilibrium constant equation like KEQ here, the concentration of the products is usually on the numerator, whereas the concentration of the starting materials are in the denominator. And so here you have the concentration of the hydronium ion times the concentration of the conjugate acid, a conjugate base, divided by the concentration of the acid times the concentration of the solvent. And again, this is all at equilibrium. Since the concentration of the solvent, which is water, is usually constant, the equation can be rearranged and a new equilibrium constant called acidity constant can be defined. And so the symbol for acid constant or acidity constant is Ka. And Ka is basically equivalent to the concentration of the hydronium ion times the concentration of the conjugate base divided by the concentration of the acid at equilibrium. And so this is Ka, and the larger the Ka value, the stronger the acid. And of course, the lower the Ka value, the weaker the acid. So hydrochloric acid, sulfuric acid, nitric acid, a lot of inorganic acids have a large value of Ka compared to organic type of acids like acetic acid or formic acid. They typically have low values of Ka. Another way to describe the strength of an acid is by looking at their pKa values. So pKa is of course related to Ka, the acidic constant, using this equation shown here. So pKa is equivalent to negative log of Ka, the acidic constant. Let's look at some of the Ka values of some organic acids. So they typically range from 10 to the negative 5 to 10 to the negative 50. And so the larger the Ka values, the stronger the acid. And the smaller the Ka value, the weaker the acid. But look at the relationship between Ka and pKa. When Ka is large, its pKa is small. And when the Ka is small, its pKa is large. So when you plug into the equation this value right here, to determine the pKa. So pKa is equivalent to negative log of, let's say, 10 to the negative 5. What you get is 5, positive 5, the pKa value. When you plug in 10 to the negative 50 into this equation, negative log of this number, you get positive 50. And so the relationship here in terms of acid strength between Ka and pKa is reversed. And so we know that the higher the Ka value, the stronger the acid. But in terms of pKa values, the higher the pKa value, the weaker the acid. So they're sort of inversely proportional to each other, Ka and pKa. If Ka is high, then its pKa is low. So lower pKa values means stronger acids. And high Ka values mean stronger acids. So again, the smaller the pKa, the stronger the acid. And here's practice problems number 7 and 8. Which compound in each pair is the stronger acid? And so when you look at the first one here, we're basically comparing the pKa values. And you know that the higher the Ka value, the stronger the acid. But what we're looking at, what's given, is the pKa value. And so if the pKa is high, then that means its Ka value is low. And so Ka is lower for this one. And so in that case, the stronger acid is the one with a lower or smaller pKa value. All right, and the second one here, we have Ka values this time. So when it comes to Ka, the higher the Ka value, the stronger the acid. And so if you're comparing the two here, this one is 10 to the negative 10 versus 10 to the negative 41. So that means that this is the larger Ka value, which is the stronger acid. The next practice problem here says use a calculator when necessary to answer the following questions. What is the pKa for each Ka values? So basically the first one here, when you plug this into the calculator, you get a pKa of positive 10 for the first one. Okay, because of the exponent. And the pKa of the second one is positive 21. And it's not really asking for which one is the stronger acid. And then the last one here, we're going to need a calculator because this is not 1. It would be easier if it was just the multiplier here with the exponent. So we're going to plug in negative log of 5.2 times 10 to the negative 5. And what we get is 4.3 for the pKa. So the third one, its pKa is 4.3. All right, well, if it was to ask which one is the stronger acid, then it would be the one with the smaller pKa value, which is this last one right here. And the second question here, we have what is the Ka for each pKa values? And so, again, the equation is pKa is equivalent to the negative log of Ka. And so if you're trying to find the Ka values, it's basically Ka equals 10 to the negative pKa. And so when you look at, let's say, the third one here, 3.2, then the Ka value is 10 to the negative 3.2, which is equal to 5.25 times 10 to the negative 4. So that would be the Ka value for the third one. For the first one here, in second, 7 and 11, the Ka is 10 to the negative 7 for this one. 10 to the negative 7. And then this one would be the exponent, 10 to the negative 11. So here's a couple of things that you should remember regarding the relationship between strong acids and bases with their conjugate acids and bases. So for example, a strong acid forms a weak conjugate base, and a strong base forms a weak conjugate acid. So let's take a look at an example. Let's say hydrochloric acid. So in water you have HCl, and when you put this in water, it gets ionized and becomes H3O plus and chloride ion. So HCl is the acid and water is the base. So of course HCl is a strong acid, so let's just label this strong acid. And then when you look at the conjugate base, that would be the chloride ion. So this is your conjugate base. So according to this information, a strong acid readily donates a proton, forming a weak conjugate base. And so hydrochloric acid is a strong acid, and its conjugate base would be considered a weak base, a weak conjugate base. So here's a table showing you the relative strength of different acids in organic chemistry. So we have hydrochloric acid, which is considered an inorganic acid, which is a strong acid, and you can tell by just looking at its pKa value. So any acids with really low pKa values are considered strong acids, and any acids with low or with high pKa values are considered weak acids. And this table also shows you the relationship between the strength of the acid and its conjugate base. So when the acid is a strong acid, then its conjugate base is extremely weak. And if the acid is weak, then its conjugate base is strong. So here we have 3 different hydrogens because they're all connected to 3 different atoms. So you have a hydrogen that's bonded to a carbon atom, you have a hydrogen that's bonded to a nitrogen atom, and a hydrogen that's bonded to an oxygen atom. And so in terms of their relative pKa values, a hydrogen that's bonded to a carbon has a greater pKa value, which tells us that this hydrogen is less acidic than this hydrogen that's bonded to a nitrogen atom, and this hydrogen is less acidic than this hydrogen that's bonded to an oxygen atom. So this is sort of related to electronegativity values. So we know that carbon is less electronegative than nitrogen, and this nitrogen is less electronegative than oxygen. And so therefore, the more electronegative oxygen is pulling most of the electrons towards itself. So this hydrogen right here is easily deprotonated, meaning you can easily remove this hydrogen compared to this hydrogen that's bonded to a nitrogen or a hydrogen that's bonded to a carbon. And so in terms of their pKa values, this would be larger than nitrogen, and then this nitrogen-hydrogen bond is stronger or has a higher pKa value than this hydrogen to oxygen bond. So let's look at this one example here. Rank the following compounds in order of increasing acidity, and then rank their conjugate bases in order of increasing basicity. And so in order to answer this question, we would have to look at their pKa values. So we can use the values from the previous table to compare their acidity. And so let's take a look. So the first one here has a pKa of 44, and then the third one has a 4.8 pKa, and the middle one, hydrochloric acid, has a pKa of -7. So we know that the lower the pKa values, the higher or the stronger the acid. And so in that case, it says rank the following compounds in order of increasing acidity. So this one right here would be the weakest. So 3, followed by this one right here, and then the highest one is hydrochloric acid. So if we were to rank them in terms of increasing acidity, 3 goes first, is less than 2, and 2 is less than 1, because hydrochloric acid is the strongest acid. And then rank their conjugate bases in order of increasing basicity. Well, if we are to look at the strength of their conjugate bases, then it would be the reverse. And so, because hydrochloric acid is the strongest acid, then its conjugate base would be the weakest base. So in that case, 1 is less than 2, and then 2 is less than 3. So this is in terms of basicity. And the first one is in terms of acidity. Here's practice problem number 9. Rank the conjugate bases of each group of acids in order of increasing basicity. So it's not asking for increasing acidity, it's asking for basicity. And so you can look at the table if you like, or you can just use a little bit of reasoning here. Like for example, nitrogen to hydrogen. So this hydrogen here that's bonded to nitrogen is more acidic compared to this carbon that's bonded to a carbon. But this hydrogen that's bonded to an oxygen is more acidic compared to this hydrogen bonded to a nitrogen. The reason why is, again, because of electronegativity. So let's look at them closely. When you draw the Lewis dot structure, you basically have this. So nitrogen versus an oxygen, and then you have carbon that's bonded to a hydrogen. And so in terms of acidity, this is the most acidic, and this one would be the least acidic. And so in terms of their basicity, then their conjugate base would be, the strength of their conjugate bases would be the reverse, right? So this would be rank number 1, right? Their conjugate base, its conjugate base would be higher than this one right here, and this would be higher than basicity of water. So when you look at their conjugate bases, the first one, the CH4 methane, would have a conjugate base that looks something like this, with a negative charge on the carbon. For the ammonia, NH3, you just subtract 1 hydrogen from it, so it becomes NH2, and 2 lone pairs on the nitrogen with a negative charge. And then for water, you now have OH minus with 3 lone pairs on the oxygen with a negative charge. And so in terms of basicity, this ion right here would be more basic than this ion, and then this ion is more basic than this hydroxide ion. So this is greater than this one, and this is greater than hydroxide. So for the second one here, again, you can use the table of pKa values if you like, or you can just use reasoning. So a triple bond is more electron rich than a double bond, and so this is actually more acidic compared to a double bond or a single bond. So in terms of acidity, this one has the highest acidity, this one is the second one, and the least acidic. And so in terms of basicity, since this one is the most acidic, its conjugate base will be the least basic. All right, so what would be the conjugate base look like for this acetylene right here? You just subtract 1 hydrogen. So 1, 2, 3, and then a lone pair, and then a negative charge on the carbon. So this is the least basic, followed by the one that contains a double bond. So that would be CH2 double bond CH with a negative charge. And then this one is less basic than a CH3 with a lone pair and a negative charge. Let's look at practice problem number 10. Consider two acids, formic acid and pivallic acid, including their pKa values. Which acid has the larger Ka value? So we know that pKa and Ka have inverse relationship. So if the pKa is high, then the Ka is low. Likewise, if the pKa is low, then Ka is high. And so we have formic acid versus pivallic acid. All right, and we're given the pKa values. The pKa of formic acid is 3.8, and the pKa for the other acid is 5.0. And so since formic acid has a lower pKa value, that means that it has a higher Ka value. And the acid that has a higher Ka value is the stronger acid. So that basically answers question C. Question C is asking which acid forms, answers question B here. It says which acid is the stronger acid? That would be the formic acid because it has a higher Ka value. Question C, which acid forms the stronger conjugate base? So the strength of the acid is basically inversely proportional to the strength of its conjugate base. So the stronger the acid, the weaker its conjugate base. The weaker the acid, the stronger its conjugate base. And so pivallic acid is the weaker acid. And so in that case, it would have the stronger conjugate base. So this one has stronger conjugate base. And the last one here, part D. When each acid is dissolved in water, for which acid does the equilibrium lie further to the right? So to answer this question, you have to go back to General Chemistry 2 and try to analyze what it means when an acid has its equilibrium lie further to the right. So what that means is you're creating more products. You're generating more products than reactants because this is equilibrium, right? You have double arrow. Reaction is going in a forward direction, and at the same time, it's also going in the reverse direction at equal rates. And so when it says equilibrium lies further to the right, that means you're creating a lot more products than you're creating reactants. And so what that means is when it comes to acids, you're generating higher concentration of the hydronium ion, H3O+. And so if you're generating a lot more H3O+, then you're also generating a lot more conjugate base and less of the acid because you're converting the acid into hydronium ion. And so in that case, this is basically what your Ka is. So if you're creating a lot more products, then the concentration of the numerator is higher. And if the concentration of hydronium is higher, then the Ka value is higher. And so the acid that generates more products or generates more hydronium ion has a higher Ka value. And that acid has its equilibrium lie further to the right. So that would be formic acid in this case. And here's practice problem number 11. Estimate the pKa values of each of the indicated bonds. So to estimate the pKa of these bonds, you would have to look at the table earlier and see if there are any bonds that are similar to these bonds shown here that are highlighted here. And so when you look at the first one, we have a nitrogen to hydrogen bond. And you look at the table that was presented earlier, and you can see that there's an NH3, ammonia. And this nitrogen to hydrogen bond in the ammonia, NH3, has a pKa value that's about 38. So that would be the pKa value of this highlighted bond here. All right, and the next one is an oxygen to hydrogen bond. And so looking at the table, you would see that one of the molecules is an alcohol. And this is basically what an alcohol is. Anything that contains an OH group that's bonded to a carbon is an alcohol. Okay, so what we have here is ethanol because it has 2 carbon atoms. And so this hydrogen to oxygen bond here, according to that table, is equivalent to about 16. So pKa is roughly 16. So in that case, this hydrogen here has a pKa of about 16 as well. And the third one here, we have an oxygen, carbon, and then this carbon is bonded to an oxygen and a hydrogen. So in that case, we have an acid, a carboxylic acid type of compound. And so you would look at the table again and find one that has a similar structure. So it's CH3COOH is one example because this is basically a COOH group right here, which is known as carboxylic acid group. All right, and so the pKa of this molecule is roughly about 5. And so in that case, this is also roughly about 5. And the last one here has 3 different types. And so when you look at the first one, this one right here, this is essentially the same as this one over here, the first one. So the pKa should be also roughly 38. And this hydrogen right here is connected to a carbon that has a double bond. So you look at one of the molecules in that table, and there's one in which the pKa is roughly 44. And the last one is similar to a methane, a CH4. So it has a pKa of about 50.